Imagine peering back through time. Not just centuries, but millions of years. What if I told you that the atmospheric CO2 levels we're seeing right now, around 410 parts per million, well, they're higher than at any point in at least the last 2 million years.
Wow, 2 million years. That really puts it in perspective.
It does, and the ocean's pH, it hasn't been this low, this acidic, in maybe 14 to 17 million years, a time when Earth was dramatically warmer and going through major extinction events.
Right, so the question becomes, what does this truly mean for us right now, for the planet, and, for future generations
Yeah.
inheriting this unprecedented shift?
Exactly. And that's really our mission today. We're going to take a deep dive into the fundamental science of climate change.
Yeah, pulling insights from, well, the big sources, the IPCC's latest reports, tons of research, but also looking back at some of the historical discoveries that got us here.
Absolutely. We want to illuminate the mechanisms, what's really driving these changes, and see the impacts already unfolding maybe in ways you haven't thought about. And then maybe most importantly, explore the choices facing us now.
Choices that will, quite literally, shape our future for millennia.
Yeah,
It's a huge responsibility.
it really is.
Yeah.
So get ready. This might reshape how you think about our planet's destiny. Let's jump right in.
Okay, so let's start at the beginning. The Earth's energy balance. It sounds simple, but it's everything, isn't it?
It really is the foundation. You can think of Earth as constantly trying to balance its energy budget. It
Yeah.
gets energy in from the sunlight that it absorbs.
Right, warming the surface.
Exactly. And then to balance that, it radiates energy back out into space, mostly as infrared heat. It's this constant balancing act.
And physics dictates this, right? There's this principle, black body radiation. Sounds technical. It does, but the idea is simple. Any object with a temperature emits radiation. The hotter it is, the more energy it radiates. Earth is no different. The Stefan Boltzmann law just puts math to that idea.
Okay. So here's the mind bender you mentioned earlier. If Earth had no atmosphere, what temperature would we be?
We'd be a frozen ball, about minus 18 degrees Celsius or 0 Fahrenheit. That's the temperature where the outgoing energy would perfectly balance the incoming sunlight with nothing getting in the way.
Minus 18°C. That's drastically different. So it's the atmosphere that makes Earth habitable.
Precisely. And that brings us to the greenhouse effect, which, gets talked about a lot, but sometimes maybe isn't fully grasped.
Yeah, people think of a literal greenhouse maybe, a glass roof.
Right, and that analogy isn't perfect. It's more subtle. It's about specific gases in the atmosphere, greenhouse gases or GHGs.
Like CO2, water vapor, methane.
Exactly. Carbon dioxide, water vapor, methane, nitrous oxide. These gases have a really neat property. They're basically transparent to incoming sunlight. The sun's visible light just zips right through them.
So the energy gets in easily, warms the ground, warms the oceans.
Yep. But then, and here's the key part. When the Earth radiates that heat back out as infrared energy, those same gases step in.
Ah, so they let sunlight in, but they don't let heat out quite so easily. Is that where the blanket idea comes from?
That's a much better analogy, I think. These GHGs absorb some of that outgoing infrared heat, and they don't just hold it, they re-radiate it in all directions.
Including back down towards Earth.
Including back down towards Earth.
Yeah.
So it's not like they trap all the heat forever, but they slow down its escape. Like adding layers of blankets, it keeps the surface warmer than it would be otherwise. The heat eventually escapes, but much slower.
Okay, a heat slowing mechanism, not a hard barrier. Makes sense. Now, who are the main players here? We hear CO2 all the time, but water vapor is a big one too, right?
Oh, absolutely. Water vapor is actually the most potent greenhouse gas by volume, absorbs across a wider range, but its concentration in the atmosphere is really dependent on temperature. It can be almost 0 or up to 4%.
Because warmer air holds more moisture?
Exactly. So if something else warms the planet slightly, the air holds more water vapor, which traps more heat, which warms the planet more.
A feedback loop, a positive feedback loop.
A really critical one. It amplifies the initial warming. Now, carbon dioxide, CO2, its concentration is much smaller, currently about 0.041%. That's up significantly from 0.028% before, say, 1870.
Still sounds tiny, 0.041%.
It does, but it's the most significant human-altered contributor. It's the main driver that kicks off that water vapor feedback loop. And then you have others like methane and F gases, increasing rapidly and very potent, even in smaller amounts.
It's still amazing how these tiny percentages have such a huge effect. Which brings us to this other concept, the emission height. What's that about?
Right, this is really fundamental to understanding how the warming happens. Think about the atmosphere getting thinner as you go up.
Okay, less dense.
Less dense. The emission height is basically the altitude where the greenhouse gases are sparse enough that the infrared heat radiating upwards can finally escape directly to space without being absorbed and re-radiated much more.
So that's like the top of the blanket, effectively, where Earth finally cools off to space.
That's a good way to think of it. And crucially, the temperature at that emission height needs to average that minus 18 degrees Celsius we talked about for Earth to be in energy balance.
Okay, so if there were no atmosphere, the emission height is the surface, and it's Anatom 18C. But with GHGs...
With GHGs, that effective escape altitude, the emission height, gets pushed higher up into the atmosphere.
And what happens higher up?
It's colder.
Yeah.
Naturally colder. That's the lapse rate. So if you push the emission height up to where it's, say, minus 25 Celsius instead of minus 18.
Then less heat is escaping than should be, because colder things radiate less energy.
Precisely. Less energy is radiating out to space from that colder, higher level than the energy coming in from the sun. You've created an energy imbalance, more energy coming in than going out.
Like a bathtub filling faster than it drains.
Exactly. And the Earth's response, the only way to restore balance is for the whole system below that emission height, the surface, the lower atmosphere, to warm up.
It warms until that new, higher emission height reaches.
Reaches that magic 18 degrees Celsius again. At that point, the outgoing energy balances the incoming energy once more, but the surface temperature is now warmer. That's the fundamental mechanism of global warming.
That is. Wow. It's counterintuitive, but makes perfect sense. So it really hinges on pushing that escape altitude higher.
It does. And it helps explain why those tiny percentages of GHGs matter so much.
Right, back to the 0.04% CO2. Why is it so powerful?
It's about the sheer activity of these molecules. A single CO2 molecule isn't just sitting there. It's absorbing and re-emitting infrared heat or bumping into other molecules and transferring energy incredibly fast, like 1,000,000 times per second.
1,000,000 times a second per molecule.
Roughly, yes. So even though there aren't that many of them compared to, say, nitrogen or oxygen, each one is working incredibly hard, constantly interacting with heat energy. A tiny number of hyperactive agents can have a huge collective effect.
Okay, that paints a picture. And the change isn't tiny anymore. From 280 ppm pre-industrial to 410 ppm in 2019.
That's a massive jump. The IPCC report states CO2 in 2019 was higher than any time in at least 2 million years, and methane and nitrous oxide, higher than any time in at least 800,000 years. This is unprecedented in human history and far beyond recent geological history, too.
Unprecedented. So the physics is clear, the GHG impact is clear, but, separating human influence from natural cycles took time. Can we trace that scientific journey a bit? This wasn't discovered yesterday.
Not at all. It's actually got a surprisingly long history. Way back in the 1820s, Joseph Fourier, a French mathematician, first proposed the idea something must be trapping heat, like a greenhouse, to explain Earth's temperature.
The 1820s. Amazing.
Then, incredibly, in 1856, an American scientist, Eunice Newton Foote, did experiments showing CO2 and water vapor trap heat more than air. She actually wrote that more CO2 would give Earth a higher temperature.
Wow, a woman scientist in the 1850s figuring that out.
It's remarkable. Then John Tyndall in Ireland, 1859, identified which gases, water vapor, CO2, methane, were the heat absorbers. He showed their specific infrared properties.
So the basic mechanism was understood quite early.
And then the big step came in 1896. Svante Arrhenius, a Swedish chemist, published the first real climate model. He calculated how much warming a doubling of CO2 would cause. His estimate, around 5-6 degrees C, was remarkably close, considering the tools he had.
That's incredible foresight. But it wasn't immediately accepted as an urgent problem.
No, not really. Some scientists thought the effect might get saturated, or the oceans would absorb it all, or it would be beneficial. It wasn't until 1938 that Guy Stewart Callendar, a British engineer, started linking the observed warming trends to the measured rise in CO2 from burning fossil fuels.
Okay, connecting the dots.
But the real scientific consensus didn't solidify until much later, maybe the late 1980s, with better models, more global data, ice core records. And today, study after study shows overwhelming agreement, like 98.7% to essentially 100% of actively publishing climate scientists agree. Humans are causing climate change.
So the scientific debate on the cause is over. It's unequivocal.
That's the word the IPCC uses. Unequivocal. Human activity is primarily burning fossil fuels, but also deforestation, some industrial processes, agriculture, have unequivocally caused global warming.
And the numbers show it. Global surface temperature, 2011-2020, was 1.1 degrees C higher than 1850-1900, almost 2 degrees Fahrenheit hotter.
Yes, and The rate of warming since 1970 is the fastest in at least the last 2,000 years. This isn't a slow, natural drift.
You mentioned earlier that most of the extra heat is going into the oceans.
Over 90% of it since 1970. The oceans are acting like a giant heat sink, which is why land surfaces have actually warmed almost twice as fast as the global average. The oceans buffer the atmospheric warming, but they pay a price in stored heat.
That's a critical point. So what about natural things? The sun, volcanoes, couldn't they be the cause?
They play a role, yes, but not in the long-term trend we're seeing. Solar cycles cause small ups and downs.
Yeah.
Big volcanic eruptions can actually cool the planet for a year or two by blocking sunlight with aerosols.
Right, like Mount Pinatubo.
Exactly. But when you filter out those short-term natural variations, the underlying persistent warming trend lines up perfectly with the rise in greenhouse gases. Natural factors alone just can't explain it. The fingerprint of human activity is clear.
Okay, so it's us. And this isn't theoretical anymore. The impacts are here now, and they're widespread. So moving from the how to the what's happening now, we're living in a world that's already warmed significantly, almost 1.5 Celsius, 2.5 Fahrenheit, since the Industrial Revolution. How does that feel or look different?
It's a fundamental shift. You know that warming stripes graphic, the blue to red bars for each year?
Yeah, it's visually very powerful.
It really shows it starkly. A clear shift from predominantly cooler blues in the past to overwhelmingly hot reds now. It's not subtle. And remember, land areas are warming almost twice as fast as the ocean average, so the changes feel even more pronounced where most people live.
And that warming feels more extreme weather, right?
Yeah.
It's not just generally warmer, it's wilder.
That's a good way to put it. Human-caused climate change is already making weather and climate extremes more frequent, more intense, or both, all around the world. We're seeing more concurrent heat waves and droughts happening together.
Like hitting regions repeatedly.
Yes. And more intense, heavy rainfall events leading to worse flooding. For hurricanes and typhoons, the evidence suggests they're likely getting more intense, with higher rainfall rates, and they're tracking further poleward than they used to. The goalposts for normal weather have shifted.
And the frozen parts of the world, the cryosphere, what's happening there? We hear a lot about melting ice.
The cryosphere is sending some of the clearest signals. Global mean sea level rose about 20 centimeters, that's 8 inches, between 1901 and 2018.
But the rate is increasing.
Dramatically. It was about 1.3 millimeters per year early last century. Between 2006 and 2018, it hit 3.7 millimeters per year. And even more recently, 2014, 2023, it looks like 4.8 centimeters per decade.
Wow. Why the acceleration?
Two main reasons. Thermal expansion, warmer water, simply takes up more space, and critically, accelerating meltwater from glaciers and the massive ice sheets in Greenland and Antarctica.
And the Arctic seems particularly sensitive, warming faster.
Much faster. 2 to 3 times the global average. This Arctic amplification is driving widespread permafrost thaw. That releases trapped greenhouse gases like methane, creating another dangerous feedback loop.
More warming leading to more emissions, leading to more warming.
Exactly. Plus, we're seeing rapid glacier retreat and a huge decline in Arctic sea ice. Less ice means less sunlight reflected back to space, lower albedo, so the darker ocean absorbs more heat. Another feedback loop, it's a cascade.
And these physical changes are hammering ecosystems.
Absolutely. We're seeing substantial and, sadly, increasingly irreversible losses across land, freshwater, ice, coastal, and ocean ecosystems. Hundreds of local species extinctions linked to heat waves, mass die-offs, think coral bleaching events wiping out huge reef areas.
Those reefs are vital nurseries for marine life.
They are. And sensitive mountain and Arctic ecosystems are being pushed towards, well, points of no return due to glacier melt and permafrost thaw. We're losing biodiversity, and the services those ecosystems provide, clean water, pollination, carbon storage, things we depend on.
And in the oceans, it's not just temperature, right? There's this other crisis, acidification.
Yes, the other CO2 problem. The ocean acts like a giant sponge, absorbing about 30% of the CO2 we release. But when CO2 dissolves in seawater, it forms carbonic acid.
Making the water more acidic, lowering the pH.
Right. And that chemical reaction also reduces the availability of carbonate ions. And those ions are absolutely crucial building blocks for marine organisms that build shells or skeletons.
Like corals, oysters?
Corals, oysters, mussels, clams, and even tiny but vital plankton called pteropods, sea butterflies. With less carbonate available, it's harder for them to build their shells. Existing shells can even start to dissolve in more acidic waters.
We're actually seeing that happen already.
Yes. Pteropod shell dissolution has been observed in places like the Southern Ocean. And since pteropods are a key food source at the base of the food web, well, you can see the potential for cascading impacts.
It ripples all the way up. Affects fish, too.
It does. Studies show increased acidity can mess with fish behavior, impairing their ability to detect predators, find suitable habitats. It affects survival. Some things, like algae or seagrass, might benefit from more CO2, but the overall picture is massive disruption.
And putting this in historical context, the projected pH levels for the end of the century.
If we continue on a high emissions path, the ocean pH could drop to around 7.8 by 2100. The last time it was that low was about 14 to 17 million years ago during the Miocene.
A period with major extinctions.
A significantly warmer world with major ecological shifts and extinctions. It just highlights the incredible speed of the change we're forcing now. We're changing ocean chemistry faster than perhaps any time in tens of millions of years.
Which brings us, inevitably, to the human cost. Health, livelihoods, displacement.
The human toll is immense and deeply unfair. About 3.3 to 3.6 billion people live in places highly vulnerable to climate change. And it's overwhelmingly the poorest and most marginalized communities, those who contributed least to the problem, who suffer the most.
Like in least developed countries, small island states.
Exactly. And the numbers are brutal. Mortality from floods, droughts, storms between 2010 and 2020 was 15 times higher in highly vulnerable regions compared to the least vulnerable. It's a profound injustice.
15 times. And beyond disasters, our health is directly impacted.
Definitely. More extreme heat means more heat stroke, cardiovascular stress. We're seeing increases in foodborne and waterborne diseases because changing temperatures and rainfall affect water quality and pathogen growth.
Vector-borne diseases, too, like malaria, dengue.
Yes, the ranges of mosquitoes and other vectors are expanding. And then there's the growing burden on mental health, the anxiety, the trauma from extreme events, the grief from losing homes, livelihoods, cultural connections to the land.
The projections for future heat stress are terrifying.
They are. By 2100, under high emissions, maybe 50% to 75% of the global population could face periods of deadly heat and humidity, making normal life incredibly difficult, even dangerous.
And the economic damage, is it hitting everywhere?
It is. We're seeing quantifiable economic damage in agriculture, forestry, fisheries, energy, tourism. And it's not just big numbers. It's people losing homes, infrastructure, income. Climate and weather extremes are increasingly driving displacement, both within countries and across borders.
Climate refugees.
Essentially, yes. And the World Bank estimates climate change could push another 120 million people into extreme poverty by 2030 if we don't act decisively on adaptation. That's just a few years away.
A stark picture of now. So let's look ahead. What do the projections tell us? What pathways are possible? Okay, looking forward, we hear about targets like 1.5 degrees or 2 degrees Celsius of warming. Why is every fraction of a degree so critical? What's the difference?
It's absolutely critical. The science is clearer than ever. Risks and impacts escalate significantly with every single increment of warming. The dangers at 1.5 degrees C are much higher than today, and at 2 degrees, they're substantially higher again.
And our understanding of these risks has actually increased. We think it's more dangerous now.
Yes, that's a key finding. The IPCC's latest assessments show that the thresholds for high or very high risk across various systems, what they call reasons for concern, are actually reached at lower levels of warming than previously thought. We're more sensitive, ecosystems are more sensitive than earlier reports suggested. That half degree between 1.5 and 2 makes a huge difference.
Does that increasing risk include tipping points, things we can't reverse?
Unfortunately, yes.
Right.
The likelihood of abrupt, irreversible changes definitely increases with more warming. These are thresholds where our system fundamentally shifts, often quite rapidly.
Like the ice sheets.
Exactly. Sustained warming between 2 degrees C and 3 degrees C could trigger the near-complete and irreversible loss of the Greenland and West Antarctic ice sheets over thousands of years. That locks in meters of sea level rise.
Several meters. That redraws coastlines globally.
Fundamentally. And higher warming also dramatically increases the risk of mass species extinction. Irreversible loss of ecosystems like coral reefs, rainforests. They just can't adapt or move fast enough. These are thresholds we desperately need to avoid crossing.
So even if we stopped all emissions today, some changes are locked in, like sea level rise?
That's the tough reality of commitment. Sea level rise is unavoidable for centuries, even millennia, because the deep oceans continue to warm and expand, and the ice sheets respond very slowly.
How much are we talking about?
Even if we limit warming to 1.5 degrees C, we're likely committed to 2 to 3 meters. That's roughly 6 to 10 feet of sea level rise over the next 2,000 years. If we hit 2 degrees C, it's more like 2 to 6 meters, maybe up to 20 feet.
Wow. So choices now directly impact coastlines thousands of years from now.
It's a staggering timescale of consequence. an intergenerational burden.
Which brings us to where we are now with global action. Are we on track? You mentioned these gaps.
Yeah, there are significant gaps. First, the emissions gap. Countries made pledges under the Paris Agreement, their nationally determined contributions, or NDCs. But even if every country fully met their pledges from back in 2021, it's likely warming would still exceed 1.5 degrees C this century, and hitting 2 degrees C would be very tough. The ambition wasn't high enough collectively.
And then there's a gap between those pledges and what's actually being done, the implementation gap.
Exactly. The policies countries had actually put in place by the end of 2020 are projected to lead to even higher emissions in 2030 than their own pledges implied. So there's a gap in ambition and a gap in actually doing what was promised.
So if we don't strengthen policies, where are we headed by 2100?
Without stronger policies, the projections point towards warming of around 3.2 degrees Celsius by 2100. That's catastrophic, frankly. Even if all current NDCs are fully implemented, we're likely looking at around 2.8 degrees C, still far above the Paris goals and deep into dangerous territory.
Okay, that's the warning. What's the alternative? What does the path to a livable future look like? It involves mitigation and adaptation, right?
Both are essential, but mitigation is paramount to limit the scale of the problem. To have a shot at 1.5 degrees C, or even 2 degrees C, the science demands rapid, deep, and immediate cuts in greenhouse gas emissions in all sectors, starting now, this decade.
Oh, rapid.
For 1.5 degrees C pathways, we need global net zero CO2 emissions by the early 2050s. For 2 degrees C, it's the early 2070s. Critically, that means global emissions need to peak by 2025 at the latest, like next year, and then decline sharply. The window is closing incredibly fast.
That sounds daunting, but the good news is we have solutions, right? Especially in energy.
Absolutely.
Yeah.
This is where there's genuine reason for optimism. The cost of renewables has plummeted. Solar and battery costs down 85% between 2010 and 2019, wind down 55%.
Leading to huge growth.
Massive growth. Solar power up more than tenfold, electric vehicles up over 100-fold in that decade. We have the tools. Electrification, energy efficiency, better urban design, circular economy approaches, carbon capture for some industries. They're viable, increasingly cheap, and ready to scale.
And what about changes in how we live? Demand-side mitigation.
Huge potential there, too. Things like shifting to sustainable, healthy diets, less meat-intensive, much more public transport, walking, cycling, energy-efficient homes and buildings. These demand-side changes in buildings, transport, and food could cut emissions in those sectors by 40–70% by 2050.
And these often come with other benefits, healthier lifestyles, cleaner air.
Massive co-benefits, better health, less pollution, more livable cities. It's not just about sacrifice, it's about building a better quality of life.
And nature itself, forests, soils.
Crucial allies. Better forest management, protecting existing ecosystems, restoring degraded lands, regenerative agriculture to store carbon in soils, cutting food waste. These natural climate solutions are vital. The science suggests conserving 30–50% of Earth's land, fresh water, and oceans is key for both biodiversity and climate resilience.
So the solutions exist, but we still face limits, especially in adapting to the changes already happening and funding gaps.
Yes, that's the hard reality. Many vulnerable communities are already hitting soft limits to adaptations, and they lack the money, the governance, the institutional capacity to implement solutions they know they need. Some ecosystems, and tragically some communities, are hitting hard limits, where adaptation just isn't possible anymore.
Like island nations losing land.
Exactly. And adaptation, even when successful, can't prevent all losses and damages. And the funding. It's nowhere near enough. Global finance for adaptation and mitigation falls way short, especially for developing countries. And the kicker. Financial flows supporting fossil fuels still exceed flows for climate solutions globally. That has to change.
That imbalance really underscores the need for a just transition, bringing us to the human element. Talking about finance brings us straight to equity. Why is focusing on climate justice, social justice, inclusion? Why is that not just morally right, but also essential for effective climate action?
Because inequality is vulnerability. Climate impacts disproportionately harm marginalized groups due to gender, ethnicity, income, historical factors like colonialism. The systems that create inequality also make people more vulnerable to climate shocks.
That 15 times higher mortality rate in vulnerable regions speaks volumes.
It does. Addressing those underlying inequities through targeted support, integrating climate adaptation into social safety nets like cash transfers, prioritizing finance for marginalized communities doesn't just reduce suffering, it builds resilience and empowers people to participate in solutions. It builds trust, which is essential for collective action.
And it acknowledges that high-income individuals and nations have disproportionately caused the problem and have a greater capacity and responsibility to act.
Precisely. There's an equity dimension to both impacts and mitigation potential. Those with high socioeconomic status have the largest carbon footprints, but also the greatest capacity to reduce them through lifestyle changes, investments, advocacy.
This all hinges on international cooperation. We have the UN Framework Convention, the Paris Agreement, but are they delivering?
They have the frameworks, yes. Nearly every country signed on. The goals are clear: prevent dangerous climate change. But global emissions have kept rising since the UNFCCC was signed in '94. And as we said, current Paris pledges aren't enough. There's a disconnect between the agreed goals and the collective action.
And finance remains a sticking point, that $100 billion promise.
A major one. That goal, $100 billion a year by 2020 from developed to developing countries, was finally met in 2023, 3 years late. That delay, and the fact that many argue the amount itself was insufficient, has eroded trust and hampered action in developing nations. It's a critical piece of the cooperation puzzle that needs strengthening.
But speaking of international frameworks, there was a huge development recently, the International Court of Justice ruling.
Absolutely massive. On July 23, 2025, the ICJ, the UN's top court, issued an advisory opinion. It basically said countries have a legal duty under international law, including the Paris Agreement, to act to prevent climate change.
A legal duty. What does that mean practically?
It means if they fail in that duty, other states could potentially sue them for non-compliance. It provides a powerful new legal basis for holding nations accountable, potentially shifting international climate politics, and strengthening climate litigation efforts worldwide. It's a potential game changer.
That's fascinating. It reminds me a bit of the Montreal Protocol success story. Different issue ozone, but huge climate benefits.
An excellent parallel. The 1987 Montreal Protocol phased out ozone-depleting chemicals like CFCs, but those CFCs were also incredibly potent greenhouse gases. So fixing the ozone hole also averted maybe 0.5 to 1 degree Celsius of additional warming we would otherwise be experiencing now.
Wow, a huge unintended climate win?
It shows that strong binding international agreements, when fully implemented, can tackle global environmental crises effectively. The climate problem is vastly more complex, tied into the whole energy system, but Montreal proves global cooperation can work.
So we have the potential for international action, legal pressure. What about public awareness? Do people grasp the scientific consensus?
There's a weird disconnect. Surveys show huge majorities globally, like 89% in a 2024 poll, want stronger political action. People are concerned. But often the public underestimates just how total the scientific consensus is on human causation, that 99-100% figure.
Why does that perception gap matter?
Because if people think scientists are still debating the cause, it can weaken the public mandate for leaders to take bold, sometimes difficult action. It allows delay tactics to seem more reasonable than they are.
Which is where activism comes in, to bridge that gap and increase pressure.
Exactly. Movements like the school strikes inspired by Greta Thunberg or civil disobedience actions by groups like Extinction Rebellion play a crucial role in raising public awareness, conveying urgency, and demanding accountability from politicians and corporations. They force the issue onto the agenda.
And litigation is another tool being used more and more.
Yes, climate litigation is exploding globally. Citizens, NGOs, even subnational governments are suing national governments and fossil fuel companies to compel stronger climate policies or seek compensation for climate damages. And the recent ICJ opinion will likely fuel even more of these cases. It's becoming a key lever for change. #outro.
Well, we've covered a huge amount of ground today, from the basic physics of warming to the global impacts we're already seeing, the future risks, the solutions we have, and the human dimension of justice and cooperation.
It really underscores that this isn't just abstract science. It's the story of our planet's present and, crucially, its future, which we are actively writing right now. The evidence laid out in these sources, particularly the IPCC reports, is just overwhelming.
It is. Human activity is driving change at a speed the Earth hasn't seen in millions of years. We've seen the mechanisms, the delicate balance being thrown off. We've seen the consequences from melting ice to stressed ecosystems to human suffering. And we've seen the escalating dangers with every fraction of a degree more warming.
And yet we've also seen the solutions. The incredible drop in renewable energy costs, the potential in how we eat and travel and build, the power of restoring nature. The pathways exist. The challenge is the speed and scale of implementation and the political will.
Which leads us to a final thought for you, our listeners. The science is clear. The window to secure a livable, sustainable future is closing incredibly fast. The choices we make collectively in this decade will echo for millennia. They'll determine the fate of ice sheets, coastlines, ecosystems, human societies.
It's a profound responsibility. Knowing what we know, seeing the solutions available, what does it mean to choose our future now?
So the question for you is, given the sheer scale of what's at stake and the tools we have at hand, what stands out to you as the most urgent action we need to take? What feels most critical, knowing that our choices today, big and small, ripple outwards, shaping the world for generations beyond imagining?